Welcome to Breadboarding. This is video 3 in the Breadboard PC series, and in this video we're going to be looking at the reset circuit and the microprocessor power supervisor circuit. I've split out the clock part of this into the next video. So in our high level plan, we can see here we're doing the reset and supervisor. We'll cover a little bit of the clock circuit in this video, but the building of the clock circuit and testing it will be in the next video. Now this is the high level plan where the first stage really is effectively building a Nanocomp Intel 8088 computer. So this is similar to the one from the 6809 series, and it will basically have an LED display and keypad, and we'll have the Nanocomp C monitor running, and will allow us to transfer programs from the PC down onto this board over the serial port, and this will allow us to develop the video controller, keyboard controller, and also then the BIOS, and hopefully then the floppy disk controller to be able to boot out of MS-DOS. Once we've got a working floppy disk MS-DOS computer, we'll then look to add an ID disk and CGA video controller, and possibly try and run an early version of Windows. Before we get into the reset and supervisor circuit, I'd just like to show you some of the chips we'll be using over the first two stages of this project. There's a few chips I still have to get for things like network adapters and sound cards, but pretty much everything we need for the first two phases of the project I will show you now. So there are quite a number of chips here. If we just zoom down and have a look at the key one really being the Intel P8088, and this is actually a 1983 chip, so copyright Intel 78 to 83. And then the other one here, this is the clock controller here. So this is not actually an Intel chip, this is a Fujitsu one, but it's the equivalent to the 8284, I think. And then this is a bus controller, and again this is an NEC chip, and this is an 8288. We then have an Intel timer, which will be added later on in the project. And then if we zoom out again, so we've got various other chips such as interrupt controllers, direct memory access controller. This one's a serial port. We've got the VIA PS2 keyboard controller that we also used in the earlier project. There's an NEC 8255 parallel port, Western Digital floppy disk controller. Then we've got the timer PC, so this is a real-time clock, the RAM and the ROM. And then up here we've got the video controller. This is the CRTC cathode ray tube controller chip. We've got our 48-pin dual port RAM, 4K RAM, that we're going to be using for the initial display adapter. And then this one here is a VGA palette chip that will allow us to output the necessary voltage levels for doing the red, green, blue video. Then we've got a variety of buffer chips over here, and these are some of the program or logic devices, both the ATF16 and the ATF22. Now what I have done, and I do say in my breadboarding tips, is I have done chip labels for all of these. So I will be putting these chip labels up on the GitHub site as well once I've got through a couple of stages of this project. And basically all we do is print these out without any scaling. We don't want to do scale to fit or anything like that in PDF. And once then we can cut these out and then stick them on the chips using a standard glue stick, so known as a Pritt stick in the UK, whatever your local preferred glue stick provider is. This is one of the recommendations, and this had come originally from a guy called Grant Searle, who's published a number of 8-bit micro project designs. And if you search for Grant Searle, you'll be able to find the chip labels that he's done, which are a bit prettier than my ones. So let's now have a look at the block diagram that we did in the introduction video. So we've got our Intel 8088 microprocessor. During this video and the next video, we're going to be adding the 14.3 megahertz clock. Now the reason why it's this rather strange frequency of clock is that this is actually 4 times the US NSTC TV color signal. And so this frequency was chosen to allow the early generation video cards to be able to produce NSTC video color output using this clock. The part that we're going to be looking at is the reset and clock circuit. Now we need to consider some aspects of the clock because the clock circuit actually does some aspects of synchronizing the reset with the main system clock. Primarily, we're going to be looking at the microprocessor monitor and supervisor circuit. So this is a MAX 1232 chip. It's a very small chip, and what it's responsible for is handling power on reset, power supply monitoring, so it will reset the processor if the power supply is unstable or goes below a certain voltage, and it also is capable of debouncing a manual reset switch. Now, some of the early PCs didn't have reset switches, but a lot of the clone PCs tended to have a reset button on the front and quite often a turbo button to increase the frequency as well. We won't be bothering with a turbo button in this one. So these are two clock circuits. One came from the PCXT schematics in the technical reference guide, and this clock circuit comes from the 8088 breadboard book. The original IBM PC had a power supply which would only allow the computer to start up via a power good signal, and basically this power good would only go high once the power supply had made sure all of the voltages it was producing were within tolerance. Only then would it let the computer power on. And over on the right hand side here, this circuit on the left hand side here is actually a switch debounce circuit. Now, by using the microprocessor supervisor circuit, it handles the switch debouncing for us, and it's actually quite a tricky thing to get right, as I found out in the previous project. Now, we're not going to be doing the clock circuit here in this part of the video. We'll do that in the next one, but we need to be aware of the outputs going to here, and in fact the reset output that goes to the rest of the breadboard computer is in fact synchronized between the signal coming in from power good and also the clock signal as well. So there are some requirements for when the reset signal changes. We're just going to have a quick look at the microprocessor monitor supervisor circuit. This is the MAX 1232. And all this does is a number of things. So it's designed to enhance circuit reliability in microprocessor systems by monitoring the power supply, monitoring software execution. So that's a watchdog feature, which I'll explain in a second, and provide a debounced manual reset input. And so the things we need to worry about is the watchdog timer basically is a mechanism that if the microprocessor kind of got stuck in some way and wasn't refreshing this signal on a certain frequency, then it would automatically reset the system. So if this was built into a bit of equipment or something like that and it was unresponsive, then it would automatically reset itself. There is a setting here to say how long we want to wait before the watchdog timer, or absence of the watchdog timer, puts it into reset. This is a connection for just the push button for reset, just goes straight to ground. And then we can also determine whether or not we want the tolerance to be 5% of the power supply or 10%. So I'm going to go with 10%, which is about 0.5 of volt. I think that means, we'll see in the sheet here, if it goes below about 4.4, 4.3 volts, then it will put the processor into reset state. So there's just a few other things I wanted to check on. One of the things I was going to do is, at the moment, this reset output here currently isn't doing anything. So I was going to hook up a LED to that, and the LED would show that the processor was in a running state. So it meant that the power was okay and it wasn't in reset. The LED needs to make sure we only draw, say, 10 or 12 milliamps maximum. So if we put a 470 ohm resistor in series with the LED, then we shouldn't draw too much current. We can see here then that the push button input for the reset is debounced active low input, so we need to tie that to ground. Ignores pulses less than 1 millisecond and will recognize inputs if it's held low for 20 milliseconds or greater. And then the time delay, by default, I think I'm just going to leave this open, so we'll get a 600 millisecond delay between resets if we don't provide the watchdog input. If we tie it to 0, then we get a slightly faster 150 milliseconds. If we tie it to 5 volts, then we get 1.2 seconds between resets. And what will happen here is, if we don't have this ST input, strobe input for the watchdog timer, then what you'll see is it's just going to go into a reset every 600 milliseconds or 150 milliseconds or 1.2 seconds. The tolerance input, what I'm going to do is just reduce the voltage, and then we'll be able to see that the red activity light is going to not come on below a certain voltage. It means it's held in reset. And the other key thing here is that the reset low output is open drain or open collector. That means that we do need to include a pull-up resistor. And this is the key bit of text here, and this is why I'm saying reading the data sheets can save a lot of time. I wasted hours and hours, if not days, on this particular issue because I didn't realise that the reset low output are open drain and sinks current only and must be pulled high with a resistor. So it's always worthwhile reading the data sheets. It will save you time. I think there's nothing else in there. Okay, so let's now build the microprocessor supervisor circuit. So first of all, I'm just going to add my breadboard buddies at the top here. What I will do is I will commentate over this and I'll speed this up so you don't have to go through every single wire being plugged in. So we'll come back when we've finished plugging this in, and I'll also then plug in the logic analyzer as well so that we'll be able to look at the signals here. So just plugging in the reset switch, that goes to ground at the top there and then will be fed into the button reset. We're just wiring up our LED, the first of 1,000 components, make sure that works. Yep, so as per 8088 book, we just plugged in the supervisor circuit, wire in the power, check the schematic to see what we need to connect. So the tolerance is going to 5 volts, which means that it will be 10%. We need to put in the push button, then we're going to wire in the pull-up resistor for the reset line, wire in the LED, and then put in the power. So that seems to be working. Now we're just going to wire in the logic analyzer lead so that we can actually check it in a minute. So I finished wiring up the power supervisor and reset circuit, and what we're just going to do now is to switch over to the logic analyzer, and we're just going to check a few things. Now, as I said, at the moment there is nothing going on the strobe input for the watchdog at the moment. What I have done is there's a pulse comes out of the logic analyzer. I think this is set at currently 100 Hertz, and what we will do is we'll wire this up to there once we've seen what happens. So let's turn this on. When the LED is on, it means the processor would be active. When it's off, it basically means we've gone into reset. So there's either a problem with the power or that the reset button is held down. If I just hold the reset button down, then you'll see that this indicates that the computer is not active. I release it, there'll be a short delay, and then it will start again. Okay, so let's have a look at the logic analyzer. Okay, so we've got the low reset, the high reset, which has also got the LED attached to it. Now, the way how this is attached is that the LED is tied to 5 volts. So when this one goes low, then it'll turn the LED on. We've got the strobe input, which at the moment is going to be low the whole time. This is the output from the logic analyzer, the square wave signal. This is the reset button. Now, hopefully when we record this, we might be able to see the switch bounce on the reset button, which is what this circuit helps to do. And then we actually use this to trigger when the 5 volts goes high on power on, then it will start actually the recording signal. And I'm currently doing 100 megahertz at 200 million samples. And what I power this on, what I will do is once the LED comes on, I'll then hit the reset button once or twice to see whether or not we can capture that. So I'm just going to power on the power supervisor circuit, and I'll just kick this off so it's waiting for the 5 volts to come up to the right level. And then within a short time after switching on the power, I'm going to press the reset button as well, so at least we can see the switch debouncing and the result of the reset. Okay, so what we can see here is if we get some timing markers, so we can see from power on that the low reset signal was in reset until after about 450 milliseconds, and then it did start, so effectively came out of reset, but then because I pressed the reset button after about half a second, and we can zoom in down to here and you can see there's a bit of switch bounce there for the reset button. There may be some switch bounce at the end as well. Doesn't happen every time, but sometimes we do get, so you can see there's certainly switch bounce at the beginning of the reset button there. And we can also see here that this is the output from the logic analyzer. So it's about a period of about 1 millisecond at the moment. Might just change that to 100 Hertz. So that means about 10 millisecond cycle. Okay, so what I'm going to do now is to adjust the voltage on the output supply, and we'll go back to looking down on the camera, and basically if I power this on and the light doesn't come on, then it means that the voltage sensing has kicked in. I'm just going to plug in a power meter so we can see what the current power levels are. Just switch this on again and we'll check to see what it's doing. So at the moment the desk power supply is set at 5 volts. You can see it's about 4.96 volts, and the flashing just means that it comes out of reset, it's active, and then because the timer times out, it then resets it again. So now I'm going to do is to change the voltage on the power supply to be 4 volts, and we'd expect that the LED will not light at all then. Okay, going to switch us on to 4 volts, so it'll probably come out about 3.96 volts on the meter. And you can see that our LED isn't lighting. So basically this is in a low power state and it's keeping the CPU in reset state. So now I'll increase this to 4.4 volts. So we'll power this on. And can see now that at 4.4 volts it's enough for the circuit to start toggling because we don't have the strobe input at the moment. If we're to change the tolerance to 5%, then the voltage that this occurred would be a bit higher, but at around 4.4 volts, then that seems to be sufficient for the power supervisor circuit to continue. So there's 2 other things we can do. So this is the pulsed output from the logic analyzer. I'm going to put that on the strobe input, and then this is also attached to the TD input, and at the moment when I power this on, we'll see that this will be flashing sort of about half a sec, 0.6 of a second. If I tie this to 5 volts, it slows down about 1.2 seconds, and if I tie this to ground, it now flashes more quickly. So that's basically just how you can adjust this sort of timeout period. So if you put it back to not attached to anything, and now if I now attach the output from the pulse generator to this, then we'll now see that it will stay on and will run. We won't get the automatic reset. And if I press the reset button, it will go off, and then shortly after releasing the reset button, it will come back on. So I'll just do the logic analyzer for this and we'll have a look at those signals. I'm just going to switch the voltage back up to 5 volts as well. So we're now just going to have a look at the signals we get once we turn this on when we have the strobe for the watchdog timer. I'll just turn this on and then I'm going to press reset a couple of times. So press reset 3 times there and we'll see what sort of signal we get out of here. Slowed the rate at which we capture the signals a little bit slower here. So what you can see here now is that we've actually got the reset output has gone low initially for our initial power on. Then I've pressed the reset button once, twice, 3 times, and we drill down here. You can see there's definitely switch bounce occurring here, which it's debouncing. And then we've got our 100 Hertz signal coming from the logic analyzer, which is going into the strobe, and this is stopping it from doing the periodic reset. So once this comes out of the 3rd reset, it just carries on running, which is what we'd expect it to do. So this power supervisor circuit and reset circuit is debouncing the reset button, and if we wanted to, we could hook up that strobe to some parallel port output and get the software to actually update that. However, I'm probably just going to connect that to one of the clock signals a little bit later, and so it will effectively disable the watchdog facilities for the moment. That all seems to be working. So we've got the reset and supervisor circuit working, and in the next video we'll be then connecting that up to the 14.3 megahertz clock and checking that the clock signals are appropriate for the 8088 processor. So thanks for watching. If you don't want to miss out on future videos, you're not already subscribed, please hit subscribe, and if you found this interesting, please hit like. It just helps to make the videos available to a wider number of people. Thanks for watching.